Do conditional probabilities pretty well today if we can. If there's a little window, I'd like to kind of get into MATLAB because I'd like to put a MATLAB question on homework too. And so we'll see if we don't do that today. We'll do it next Monday. Either way. But so let's let the games begin. Let me see. Conditional probability. Probabilities. Right? The probability of B given A. Okay. Is A has or with certainty will occur. Certainty will occur. Okay. So probability of B given A is the probability of B given A has or will. As will occur. We saw last class kind of the fundamentally, I don't know what's happened to this board. Okay. We saw last class kind of the fundamental picture. The probability of B given A is, don't forget, we now have taken whatever your original sample space had been, and it now gets reduced simply to A because we already know that everything outside of A is immaterial, right? And so the only way B can occur in the presence of A is in that intersection, right? So that's where that numerator was the probability of A and B over the probability of the thing you conditioned on, A. Okay? Good. And so if you are dealt 3 cards from a standard deck, standard deck, right? What's the probability they are all hearts? All hearts. Right? And so, let's think about that for a little bit. Okay? And by the way, if you're not familiar with a deck of cards, more power to you. A standard deck has 52 cards, of which there are 13 of each type. There are 13 hearts, 13 diamonds, what else? 13 spades, and 13 clubs. Okay? Right. So, if you're dealt 3 cards, and by the way, it seems a little bit self-evident when it comes to cards, but I will make sure I write it here, without replacement. Without replacement. Okay? Good. And so, let me see. By the way, we could draw a big tree about this. By the way, we can consolidate things together. When I say a big tree, I don't know if it needs to be actually all that big because we can, since this question is dealing with hearts, we could classify every card as either a heart or not a heart, right? And so it's not like you've got 52 branches all pointing out and branching out, And so, but it is without replacement, okay? So in other words, the probability now, and maybe I will just start this, okay? That first card could either be a heart or it might not be a heart, okay? Whoops. I like doing my hard examples. And so, given this, You know, as long as your cards don't have tears or bends in them and things like that, what's the probability that first card is a heart? 13 out of 52. Are you in agreement? 13 out of 52, right? Right? I'll put a subscript 1 there. Probability is 13 over 52, by the way. You can fill in the complement down there, okay? And then don't forget that as I go to start to plot my second card selection on here, I'm going to start from each of those terminal points, so there's prior knowledge being gained in so doing, right? And so the second card here might either be a heart, or it might not, of course, right? But it's in presence of that additional information, right? The first one was a heart, given the first one was a heart, okay? Again, we can fill those out, right? At least the top branch for ease to make this as simple as we can. What is the conditional probability that the second card is a heart, given you have a heart? 12 out of 51. 12 out of 51. I agree with that, right? Whoops. I agree with you, but it's not what I wrote. Okay. And the main reason I wanted to start with this, because I thought it was a bit of a nice launching point, okay, is as I go to draw that third selection, okay, what is my prior knowledge right here where the pen is? So far I've drawn 2 hearts, right? Or in other words, my prior, the third could be a heart, given that sentence, the prior 2 were hearts. Is heart 1 intersect heart 2, isn't it? Right? Heart 1 intersect heart 2, right? Right? And the probability there is, well, I don't have to beat you up about that. If that was 13 over 52 and that card was removed and that was 12 over 51, that's 11 over 50, right? And so, 11 over 50. So, the probability that all 3 are hearts, and heart 3 is the probability the first card is a heart times the probability the second is a heart given the first was a heart times the probability the third is a heart given the first 2 were hearts. And notationally, that's how that would get written, right? You see what I mean there, particularly about that third leg there, okay? And it is what we said, multiplies across the branches, okay? 13 over 52, 12 over 51, 11 over 50, whatever that turns out to be, okay? Good. Okay. Let's see. Let's tinker with another little warm-up for a minute here, okay? So.
And I know this is a given, but we're assuming that it's been randomly shuffled, right?
And we should hope so.
Okay.
Yeah. That is always the question, though, isn't it? Yes. Or if you're really working with 52 or maybe 53 cards.
I actually do have a question about
Please.
that problem. So if before the last line, for P heart 1 would be intersected with the next one. So intersected with heart 2, intersected with heart
Say that
3.
again? Sorry.
So but in the second last line, right, in the line before the last, in the probability of the
Right here?
heart, yes. That
Oh,
one.
yes.
If
Yes.
everything was, if everything was unioned instead of intersected,
That's a completely
they
different
would be
story.
added. It would be addition, right? 13.
I don't know.
Because don't
Do you want to? What if that question was? Okay, way to go. Way to mess up my daily plan. What if that question was What's the probability that none of them are hearts?
Look
Right?
at the other branch. Oh, but there's other branches in which none of them are hearts.
Yeah, what would be a good question? None of them are hearts, or at least one of them is a heart. None of them is hearts is pretty easy, right? Right? Because then you're just weaning your way down that bottom branch, and that's all easy. How about at least one is a heart?
There's other branches to contend with that.
Yeah, you got, yeah. Find the probability you get, oh yeah, you wanted a union.
Yes.
Okay, get at least one heart. Okay. By the way, that is generally, please.
Could you move your
Oh, yeah,
production touch?
sorry.
Thank you so much.
Sorry about that. You found my kryptonite. Okay, yeah. And so, at least one heart. I'm gonna kind of write this out the long way, okay? And as you said, the probability, and you know, this is actually kind of a good example because we're going to see kind of more and more cases quite similar to this, right? That at least one heart is the probability of heart 1 or heart 2 or heart 3, right? And so, yeah, this might be kind of tricky. I'm not 100% sure, right? Doing it directly might be kind of tricky, and when I say kind of tricky, what I mean is it has a lot of moving parts. You know, not that it's hard, it's just you got to be careful, right? But when you get a union like this and it gets particularly nasty like this, you know, when you're thinking about it, you've got all these there's event 1, the first heart, there's your second heart, there's your third heart. Looking at all of that, at least one heart, might be easier to look out here. You know what I mean? Yeah.
And because it's replacement, all 3 events are not equally likely, right?
No, they're
so
not.
they don't just add.
Yeah, you got to be super careful about some of that, right? And the whole adding and what, you know, now you're getting into disjoint cases, and you know, if that can be a little tricky. But notice something that one can do, right? The probability of at least one heart is 1 minus the probability of the complement of at least one heart.
Which is no hearts.
I don't know, but it might be.
Oh.
It might be, you know? But let's take a step and see if it is, right? So, using complements. It's 1 minus the probability that that's simply not the case. Complement. Okay. Do you like that? Do you agree with that?
Yeah.
Right? Okay. Now, I'm not disputing what you're saying, but I'm not sure you were telling me it with the greatest confidence. You know? Can I do anything to this?
You can distribute out the complement.
I can use De Morgan's law, right? I said, when we first mentioned De Morgan's law, I was like, oh yeah, we're going to be using De Morgan's law all the time, kind of almost without even speaking about it, right? Let's use De Morgan's law right here, right? So that is 1 minus the probability of De Morgan. Okay? What does tell me what that is using De Morgan's law.
The complement of part 1 and the complement of
Part
part
1
2.
complement and part 2 complement and part 3 complement. Now can you say with more confidence that the complement of at least one heart is no hearts?
Yes.
Now see, that's where De Morgan's law. Now that we've got De Morgan's law, see, the thing is once we get these multiplication rules for conditional probabilities and in a few minutes for independence, then an intersection question like this is dramatically easier than that, right? Because now that's 1 minus the probability the first one is not a heart times the probability the second is not a heart, given the first was not a heart, right? Times the probability the third is not a heart, given neither of the first two were hearts.
That was my question.
Do you see what I'm saying there? Right? Now, this is simply, well, I shouldn't say this is simply, I should let you tell me what the simply part is. What's the probability the first one's not a heart?
39 out of 52.
39 out of 52. And then we create our descending pattern, right? Right? 39 over 52, 38 over 51, 37 over 50. You see what I'm saying? Do you like that?
I like that.
Is that? Yeah. Interesting.
That was my question, and you answered it. It's not as simple as just flipping the sign. No.
Well, call it what you want. Call it what you want. Okay, so, what's the probability that exactly, oh, please, I'm sorry about that. You've had your hand up for 10 minutes here.
So can I say the whole probability minus 13 or 12 over 52?
Only for that first card.
Oh.
Only for the first one, but then once that first card gets removed, that changes for the second selection.
Two others.
You see what I mean? Yeah. And, I mean, the extremes are easy, At least one is associated with kind of none of the other, so forth and so forth. What if the question was, what's the probability that exactly one of the three is a heart?
Ooh.
Please.
Right, so like sort of related, I have a question about like the union sign. We have like one that means and one that means like or, and or.
Yeah.
Is there one that's like an exclusive or? Is there one that means like?
Different textbooks do have things like symmetric differences. I've seen a triangle used for that.
Okay.
An exclusive or, the way I've described an exclusive or is like in if you have it's trouble on top of trouble. Let me see. Okay. I got 2 pens. What's the probability one of them works? Okay. If you've got an A and you've got a B and you want that exclusive or, which would be this and that, a way to depict that. Now, like I said, there are different textbooks because it comes up, So different textbooks do use some different notation, but I've been avoiding those because they kind of miss the underlying idea. And the underlying idea is that this is A intersect not B, right? And this is B intersect not A, and we're taking the union between them. You know what I mean?
That makes total sense.
Yeah.
Thank you so much.
So the probability that only one is a heart, if I'm following all of this correctly, would be the probability the first one is a heart. I don't know if this is going to be or and, but the next one will be the probability the second one is a heart, given the first one was not a heart.
There you go.
And the third one would be the probability the third one is a heart, given the first two were not
There
hearts.
you go. I like that general idea. And so let me write a little bit of that down. This is kind of good. See, am I on here?
This problem is cute and I like it.
Remember, you called it cute.
I like all that.
Find the probability exactly one of the three is a heart. Okay, okay, and you said, you know, for instance, find the probability that the first is a heart, followed by something that's not a heart, followed by something that's not a heart. Right? Right, if I heard that right?
Yeah.
Yeah, yeah. But here's the rub about that. Is that the only way you can end up with one heart?
No.
Couldn't it have been the second card?
Yes.
Or the third card?
Yes.
You see? And so, and those three cases are disjoint from each other, right? So that's plus the probability the first is not a heart, but maybe the second is, then the third is not, right? And the third possibility is that the first two are not hearts, but the third one was. Right?
Yes.
Now your comment about expressing these as a string of conditional probabilities, spot on, right? For each of those three cases, right? Right? So this one here is, you know, just for example, this is the probability the first is a heart times the probability the second is not a heart, right? Right, whoops, the second is not a heart given the first was a heart times the probability the third, oh, I need a complement there. The third heart is not a heart, given the first one was, but the second one wasn't. Does that sound right? Right? And then you do the same for that and do the same for that. By the way, this is 13 over 52, right?
Yeah.
Then what's the probability the second is not a heart given you're looking at a heart?
39 over 51.
39 over 51. Do we like that? Right? 39 over 51. And the last but not least, the third one is not a heart, given you've got one heart and one not heart in your hand. 38 over 50, right? 38 over 50. Now, if you do the same for each of these, and let's do one more down here, and you'll see, okay? Here's the probability the first is not a heart, probability the second is a heart. I should subscript them given the first was not, times the probability the third is not.
Shouldn't these all come out to the same thing?
That's the point. Yes, they should. It's just a reordering of the numbers in the numerator. Yes, exactly right. Right? One complement intersect part 2, right? And you see that this is 39 over 52. This one here, you still have all 13 hearts, but you only are drawing from a pool of 51. This one here, you've already removed one not heart, so you've got a 38 over 50, right? You see that those are equal to each other, right? That third one would also be equal as well, and you end up with 3 times 13, 52, 39, 50, whoops, 38, 50. Does that make sense? Right? And if you have a little combinatorics, that 3 is counting the number of ways that you can produce exactly one heart out of 3 cards. You see what I'm saying there? Right? Right? All right. How's that one feel? Still cute? Okay. Good. Conditional probability. How about, I don't know. Andy, you gotta move on. Suppose. We try to make, I don't know if this is a quick example, but we'll try to make this a quick example. Okay? So here, example, the given the probabilities associated with, I'll call it, I'm no biologist, genetic markers, I'll just call them 1, 2, and 3. 2 and 3. Okay, can we see that? So let's suggest the probability of having genetic marker 1 is 0.08. Okay. The probability, i.e., the probability of having genetic marker 1. Okay? And the probability of having genetic marker 2, I'm saying, is 0.10. Probability of having genetic marker 3 is 0.12. Okay? Furthermore, the probability of having both genetic markers 1 and 2, right, is 0.03. Okay? The probability of having markers 1 and 3 is 0.02. 2% of the population have those two markers. The probability of having markers 2 and 3, let's see, where did I go there? 0.025. Right? And the probability of having all 3 markers is 0.005. Okay? Okay? Let's find the probability of 1 and 3 complement. What is, by the way, in a sentence, what is that 1 intersect complement of 3 in a sentence? How would you even describe that?
The probability that you have marker 1 and you do not have marker 3.
There you go. Do you like that? You like that? Good, good. And so does anybody see how we could tease that out? Tease that out.
When in doubt, De Morgan?
It's always worth a try, you know? Yeah. Well, don't forget that, and I don't know if this sounds too mathy for me to say, but any event can be decomposed by another event, right? So in other words, every person who has marker 1 either has marker 3 or they do not have marker 3, right? Is that, kind of a silly but fair statement, right? Right? So, and nobody can both have and not have marker 3, right? Right? So that means, so basically, by the way, looking at that, and by the way, this would be kind of the easy way to do this problem. Wasn't really what I was planning, but 1, 2, and 3, right? Everyone here either has marker 3, i.e. they're in there, or there, or they don't, right? So let's take marker 1 and let's decompose it by whether they do or do not have marker 3, right? Specifically, since event 1 is 1 and 3, or 1 and not 3, right? You see what I'm saying there? Kind of getting to these are disjoint, right? So the probability of having marker 1, which is 0.08, is the probability of having 1 and 3, right, which is also given right there somewhere, right, plus the probability of 1 and not 3. Does that make sense? Right. And so, right, the probability of 1 and not 3, right, is the probability of 1 minus the probability of having 1 and 3. Does that make sense? Or 0.08 minus where is it? Right there, 0.02. Or 0.06, i.e. in this particular population, 6% of this population have marker 1 but not marker 3. Right? Right? Does that work?
Okay, to see if I follow this. So we start with the probability of having 1 and not having 3, which we deconstruct. We want to find, in the lovely diagram there, the area of 1 that does not intersect the area of 3.
There you go.
So we decompose 1 into its two parts, which is the part where 1
There.
intersects 3,
That's right.
and
That's right.
or the part of it where 1 does not intersect 3.
Exactly right. So you're starting with that oval right there, right? And you need to find that part of it, right? But you know that part of it, and you know the whole. Exactly right. Exactly right. So
So I guess my follow-up question then is, because I thought in order to add, one of the rules was they had to be equally likely.
No.
Or is it they just need to be
they
disjoint?
need to be disjoint.
Okay.
Yeah. You know, for instance, suppose 40% of the population say their favorite soft drink is Coke, and 30% say their favorite soft drink is Pepsi. What's the probability a random person would say their favorite soft drink is either Coke or Pepsi? Well, they're disjoint, so those just add 4 to 0.7.
Gotcha.
Make sense? Yeah. And so, by the way, there was a method to this madness, and we'll let this get a little more interesting in a second, but B, right, given a person or a random person or a random thing, person does not have marker 3, what's the probability they do have marker 1? Oh, sorry about that. There you go. Right.
So isn't this the conditional probability?
Yes, what are we conditioning on?
The part of the circle of 3 that's inside of 1?
I don't know about that, but in terms of markers,
Oh, they don't have 3.
don't have 3. So given they don't have marker 3, what's the probability they do have marker 1? Right. And quite frankly, isn't that simply just the probability of 1 and not 3? Which that's why I eased us in here slowly for what that numerator is, over the probability of not having marker 3. You like that? Okay. Good. And we've seen here that the probability of having marker 1 but not marker 3 is 0.06. Right? And what's the probability of not having marker 3?
It's 0.88.
0.88. The complement of having marker 3, right, is that there is 1 minus the probability of 3, right? Or 1 minus 0.12. What's that all come out to? I don't know. 0.06. 0.06 divided by 0.88, or 0.068. 0.068. Good. So in other words, based on these numbers, right? among people or whatever your population is, I don't mean to always talk about people, who do not have marker 3, 6.8% of them have marker 1. See what I'm saying there? Okay. Please.
And then because these numbers are different, we would say that they are mathematically dependent.
Dependent, yes,
Okay.
yes. Well, that was gonna be my next question.
Sorry.
Yes, no, perfect, I like it. That shows the synchronicity, right? Yeah. When you see that, and even if it's subtle, you know, in the general population, 8%, but if you look at those who don't have marker 3, it changes to a little under 7%. You know, clearly I shouldn't say clearly, but you see how it feels there's some association between markers 1 and markers 3. I'm not saying that it's one's causing the other, but I am saying that those demographics change a little bit in there, you see? Yeah. And let's just tackle this one. What's one more of these? We'll try to not make it the hardest. Oh, how about that? How about, okay, so make it a little bit more interesting. Okay. Given well, that might be hard. Oh no. Yeah. Given, this would be easy. Okay. A subject, a random subject, has both markers 2 and 3. What's the probability they also have marker 1? I say the solution to this is pretty straightforward, though admittedly the kind of thinking it through, it might not be, right? So given they have both markers 2 and markers 3, what's the probability they also have marker 1? Would have been an interesting question. Well, notationally anyways, it's the probability given they've got markers 2 and markers 3, right, that they also have markers 1. Right? Well, going literally by the equation, the definition of conditional probabilities, right, that's the probability of having 1 and either 2 and 3, all over the probability of having 2 and 3. Okay? And where's our original numbers here? Do we feel, are those original numbers, or are those numbers that we need just directly off of there?
I mean, we do need at least one of them.
We need, now this one right here, right? Do I really need those ladders, since this is an intersection and that's an intersection, do I really need those parentheses?
No.
No? So that numerator is the probability of having all 3 markers, right, which we've got, versus, and the denominator is the probability of having both 2 and 3, which I think we've got that too. So that's what I mean by this one comes out fairly nicely, 0.025, and I think, oh, is that 0.25? Isn't it? Is that 0.25? 0.005 divided by 0.025 means, 0.2. Right, 0.2, yeah. 0.2. Right? Interesting, interesting. So 20% of those who have both markers 2 and 3 also have that marker 1. Please.
So in the event we were not given the probability of having 1 and 2 and 3, is that something we would have been able to find given the other information in the problem?
If I had given us just that,
Yeah,
the answer is no.
okay.
Because frankly, you don't know if these things are independent
Okay.
or if they're dependent, and you don't know the weights of the dependencies if they are there, right? So no, that was actually a vital piece of information, okay? You know? Now a question that I think would take us a little bit too much time, but I was thinking about it, you know, is given that somebody has either marker 1 or markers 2 or marker 3, what's the probability they have marker 1? Maybe I'll leave you to think about that, or maybe I wonder, right? Given a subject has either marker 2 or marker 3, what's the probability they have marker 1? Right? Now for that, okay, for this, I think I would probably resort to that Venn diagram and figure out what's really going on. Because don't forget, in that Venn diagram, this here is the probability of 1 given 2 or 3, right? So that's the probability of 1 and either 2 or 3, okay? So it might take a little more untangling, okay, over the probability of 2 or 3, right? And to help with that, at least maybe we won't punch it out unless it seems obvious, but there's a 1, there's a 2, right? There is a 3, right? Oh, I am still on the board, okay. Might be on the board, I'm kind of off the page. That denominator is this, 2 or 3. Right? And that numerator, oh, we can do all of this, and that numerator is that. We in agreement on that?
Yes.
Did I draw that about right? Right? And again, inquisitive minds could wrap that, could take care of that. Don't forget that the probability of 2 or 3 is the probability of 2 plus the probability of 3, but they're not disjoint, minus the probability of 2 and 3, right? So 0.1 plus 0.12 minus 2 and 3, 0.025, that gives you something like 0.22 minus 0.025, something like a 0.195, okay? And, interesting. The probability of 1 and either 2 or 3, okay? Now, for that, I'm guessing, by the way, am I writing big enough? Can everybody see that all right? I think I'm getting myself engrossed in the problem and forgetting that there's an audience out there, right? Right? Yeah, you can tinker with that. You could yank that apart. I'm also noticing when I look at the Venn diagram, that isn't that the intersection of 1 and 2 plus the intersection of 1 and 3, and then we've double counted the three-way intersection in the middle. So do you like that? I'm kind of feeling I've got a probability of 1 and 2 plus the probability of 1 and 3 minus the probability of all three of them. Does that sound right to you? Did I say that right? You know? And if we like that, that's a 0.03 plus 0.02 minus a 0.005, right? Somewhere in the order of 0.045. Does that look right? And so the answer up here looks to me like 0.045 over 0.195, or about 45 divided by 195, about a 0.231, right? So if you have either marker 2 or 3, then the probability, the likelihood or the chances of having marker 1 is about a 23%.
Steals from the original, most likely gives
How's
us
that
one.
feel? We like that example? Not as cute as the cards, but you know. Okay. So, you're seeing where a little bit of where this wants to go, and you can imagine that this problem set could go on forever. Okay. Well, let's start thinking about some things here. Okay. So conditional probabilities. They're always kind of a segue into Bayes' rule. Okay. Now, let's see, so that I'm on my red line. There. I think this red line has to stay, actually, you know? Okay. And so, Here is, so we're going to go into kind of a big concept for us called Bayes' rule, okay? And I will tell you that in this course, Bayes' rule, we're going to keep revisiting it with each new idea we mention, okay? And here's the idea, here is kind of the mechanism that makes Bayes' rule work, okay? And I'll call this law of total probability. Total probability and Bayes' rule. Okay? Now, here is kind of the key feature of conditional probabilities. Okay? Is that the probability of B given A is the probability of both of them divided by the probability of A. Right? And so, the probability of A and B is the probability of A times the probability of B given A. Right? Well, this kind of, it's not really true, but this kind of has that flavor to it that the A comes before the B. You know, that's not necessarily true, but it kind of has that feel, right? But you notice also, there is really nothing special between A's and B's and what's first and what's second, you know? Is what's the probability of A given B, right? Well, that's the probability of A and B, but you're dividing by the thing you conditioned on, which in this case is B, right? And so, that numerator, the probability of A and B, could similarly be expressed as the probability of B times the probability of A given B. Okay? So we have these two different ways the probability of that intersection can get expressed, by conditioning on one event or by conditioning on the other event. Bayes' rule, what Bayes' rule intrinsically does is it switches what you're conditioning on in it. Okay? So that's going to be a key in a second. Okay? Before we get there, let's mention the law of total probability. Total probability. Okay? Now to do that, we should introduce something. I haven't mentioned it yet. It was in the first section, but a partition. A partition. Okay? Let change colors. Let A1, A2, dot, dot, dot be a sequence of events such that, by the way, it can be a finite collection, but it can also be a listable collection of sets. Okay? Be a sequence of events such that, one, they're pairwise disjoint. Pairwise disjoint, i.e., AI intersect AJ is the empty set for all IJ as long as I and J differ. I not equal to J. Okay? Okay? By, yes. Okay, we got to do that some point. Okay, and if I take the union of them, I goes from 1 to infinity. If I take a union of all those pairwise disjoint sets, I reproduce the sample space. Okay, so a partition, if this is our sample space, our partition is some collection of non-overlapping sets that cover the whole sample space. You see? You know, like we do it all the time. The United States can be partitioned into the 50 states, or people in the US can be partitioned by income bracket or ethnicity or any of the other kinds of questions we tend to ask. But a partition is this segmenting of the sample space in a way that it covers the sample space and there's no overlap, right? So that, well, I forgot the punchline. A1, A2, dot, dot, dot is called a partition of that sample space. Okay? Okay. Yeah. Term you're probably somewhat familiar with. Now. To get to the law of total probability, we'll start with such a partition. So I'll say let A1, A2, dot, dot be a partition of the sample space. Let B be another event. Okay? Oh, I'm off my red line. There we go. Okay. So now that same picture, there's my sample space. Here is some sort of a decomposition. A2, A3, A4, dot, 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 A5, dot, dot, dot. And now there's some other event B. Okay? You know? For instance, like maybe our sample space is the United States and we're partitioning by state, and B is a person is unemployed, right? There are unemployed people in Washington, there are unemployed people in Oregon, there are unemployed people in California, so forth and so on. You see what I'm saying there, right? Right? And so this event B can be decomposed by that partition, right? B is A1 and B, or A2 and B, or A3 and B, or dot, dot, dot. Right? Do you agree with that? Right? That this oval B is the union of this piece, unioned with this piece, unioned with this piece, unioned with this piece, so forth and so on. Does that make sense?
And for a partition, the events have to be separate. They can't be the complement of an event.
Sure, A complement form a partition.
Okay.
Oregon is completely partitioned by the union of employed people and unemployed people.
So you could describe a partition by saying everyone is either A or not that.
Well, that would be a specific type of partition.
Gotcha.
You know, kind of like a Macintosh apple.
Why do we OR them?
What's that?
Why do we OR them?
Because B is this whole thing here, so it's, it's gotta be in this piece right there, right? And so that's A1 intersect B, right? But it could also be in that piece there, which is A2, right? So isn't that part of B A1 and B, or A2 and B?
Yes, but you're considering both of those spaces still?
Yes, I'm taking the population of unemployed people and I'm breaking them up into who lives in Oregon, who lives in Washington, and who lives in California. But to get all my unemployed people back, I take the union of all those sets,
Okay,
right?
yeah.
Does B have to be an event that touches every?
No,
A?
it doesn't.
Cool.
For instance, and now that does raise some interesting questions because in a discrete math class, they very often say that those have to be non-empty sets. But think about something like it's been in the news lately that measles are on the uprise, right? There are measles cases in California, Oregon, Washington, but there are none in Idaho and there are none in Nevada. You see what I'm saying? So yeah, it does not have to intersect every single one of those sets. In fact, I'd venture to say that in those omissions, there's a lot of information, right? Because it's with that very information, we're seeing how incidence of measles is propagating across the country, Yes, so you're absolutely right. Any one of these or could be empty sets in there. Yeah. Now, so we like the intersections, we like the unions. We're working on the unions. Okay, next question. Is this a union of a bunch of disjoint pieces? Yeah, because the original AIs are disjoint from each other. Subsets of them have to also be disjoint. Fair statement, right? So these are all disjoint, right? And now, so thus, the probability of B is the sum, right? As I goes from 1 to, usually there's an upper end, but I'm leaving it open-ended because it's also true, of the probability of AI and B. And so now comes the conditional probability where AI and B, the probability of it is the probability of AI times the probability of B given AI. So that brings us to the probability of B is the sum, I goes from 1 to whatever the top is, of the probability of being in the partition slice times the probability of B given you're in that partition slice. That equation right there is known as the law of total probability. And so it took us a little bit, it took us more than a minute to, can we do one example of this so I don't leave you on your break scratching your head for 10 minutes, you know? And so, and truth is, this takes a little bit of talking through, but the reason it takes talking through is not because of the concept, it's because of the symbols, okay? Let's do an example, and you're gonna realize that, all he's talking about is a weighted average. That's all it is. Okay, let me show you what I mean. In a short example here, and hope it's not the same one I posted from last quarter, but we'll see. Suppose a company purchases a particular component from 3 suppliers. Call them A, B, and C. Okay? Furthermore, okay, let's say, 70% of the purchases come from supplier A. Suppose that 20% of the purchases come from supplier B. Suppose that the remaining 10% of the purchases of these components comes from supplier C. Okay? Okay? Now, the money here is I just partitioned all the components I have in stock based on where they came from. Right?
So I know this probably goes without saying, but for a partition to be a partition, the sum of all of them should be 1.
That's right, because the union has to achieve what? The whole sample space again. Yes, exactly right. Exactly right. Right? And so that is kind of, you see that these are disjoint. No single component can come from more than one supplier, right? You also see that it exhaustively covers all the components we have in stock. So that's a great statement there. We see from here that the probability that a random part comes from supplier A is 0.7. A random part from supplier B, the probability a random part comes from supplier B is 0.2, and the remainder come from supplier C. Right? Okay. Most parts are good. However, some components are defective. Okay? Okay. Of those purchased from supplier A, let's say 1% is defective. Okay. Of those purchased from supplier B, 3% are defective, right? And of those purchased from supplier C, 8% are defective. Which is probably why we only get 10% of our stock from supplier C, right? Okay. What percent of all the part? If I randomly pick a part out of stock, not knowing what supplier it came from, what's the probability it's defective?
12%?
I don't know.
We need to do a summation.
Right. And so one part is selected from stock. What's the probability it is defective? Right? Now, as we work in here, okay, let's call defect D, okay? Do we see that these three lines here, of those purchased from supplier A or supplier B or supplier C, those are all conditional probabilities, right? Right? So from this line here, I'm seeing if a part comes from supplier A, the probability it's defective is 0.01, right? I'm also seeing that if a part comes from supplier B, the probability it's defective is 0.03. If it comes from supplier C, the probability it's defective is, what did I say, 0.08, right? Right? And in my question here, okay, we need to find what's the probability of D. You see how this lays this is this picture. We've got our decomposition, right? Only between these three suppliers, right? Right? We have this other overarching event, the parts are defective, right? We basically want to take the defect rates, weight them by how much we use them, and that's how that weighted average works, right? That's all that equation says, right? And so, the law of total probability. Using the law of total probability, okay? And I'm going to write out, a couple extra steps in here just to kind of ease my own mind. But first off, seeing what's happening here, the probability of D, okay, looking at those defective parts, okay, right, is the probability that it came from supplier A and it's defective, or it came from supplier B and it's defective, or it came from supplier C and it's defective, right? And why am I just adding those up? Because they're disjoint. Right? Now we add our conditional probabilities in here, right? We re-express these intersections where we can incorporate the information as it's provided for us. Specifically, it's the probability of purchasing from supplier A times the probability it's defective if you purchase from supplier A, plus the probability of purchasing from B, plus the probability it's defective if you purchased from B, right? Last but not least, the probability of getting it from supplier C times the probability of being defective if you got it from supplier C. You see, and that's the law of total probability written out right there. And you see, using these numbers, 70% of my stock comes from supplier A, so we're going to weight it more heavily because a lot of stock comes from there. And of those from supplier A, only 1% is defective, right? We purchase another 20% of parts from supplier B, and in that pool, what did we say here? 3% are defective, right? Last but not least, there's supplier C, our emergency supplier, but 8% is defective. Does that seem okay for us? Just seeing that picture like that, right? And then I don't know what this turns out to be. 0.7 times point. Oh, I should be able to do this in my head, shouldn't I? Sure. Could if people weren't looking at me. I get about a 0.021, 2.1%. Anybody else check that? Yep. 0.021. Okay. So the probability of selecting a random part without regard to supplier, and so we'd conclude that of all the stock, if there's a lot of stock in there, 2.1% of the stock is defective in there. How's that feel? Does that feel okay? Law of total probability is not bad. It's not bad. Okay, Bayes' rule, we're going to take a break here. We won't have much time left, but here's what Bayes' rule does. Every time, it's, this is how you identify it. Bayes' rule does and will change the conditionality from being based on the partition pieces to being based on the event, right? This is, if I buy from supplier 1, the defect rate is this. If I buy from supplier 2, the defect rate is this. A Bayes' rule question would say this: I just picked up a part. The part is defective. What's the probability it came from supplier C? Right? See how I changed the conditionality? So now we're conditioning on the quality of the part rather than the supplier? That's Bayes' rule. Let's take a break. So about 10 minutes. Is that good? How you doing?
Could you just zoom out a little bit so I can see the first?
You know what? Let me see. I think I can. I didn't even try it. Am I getting better?
That works, yeah.
Yeah. And if